Do you think it resides in the corridors of the Parliament? Or perhaps in wealth and riches of this world? Bah! That is mere pittance compared to the powers of the universe, the laws of reality, that hold so much more that we cannot even comprehend, of powers hidden in other dimensions that overlap the only ones you can see. I exist in such a dimension, a place mere moments away from the bustling corridors of the Parliament, yet entirely unknown to those who walk its halls. These hidden dimensions, teeming with energies and entities beyond comprehension, hold a power that dwarfs any earthly authority. The very air shimmers with the presence of forces unseen and unheard by the ordinary senses, revealing a world parallel to our own, rich with the untapped potential of the cosmos. As I sit here, cloaked in the solitude of my arcane study, surrounded by ancient tomes and flickering candlelight, I invite you to journey back to a fateful evening, an evening that altered the course of my scholarly pursuits and introduced me to a being from another realm. I remember that evening well. Shelves brimming with ancient tomes and mystical artifacts surrounded my central workbench, which was cluttered with experimental devices and bubbling vials. The air was thick with the scent of incense, mingling with the faint hum of energy that permeated the room. Here, in this sacred space, I sought to uncover the deeper truths of the universe, blending old-world magic with modern science, in a quest for ultimate understanding. My experiment was to be a simple one, or so I believed. With a concoction of elderberry ink and a whisper of the wind, captured during the last solstice, I set out to breach the veil between dimensions. A harmless peek into the unknown, I assured myself. But as is the nature of such experiments, the outcome was anything but predictable. My incantations filled the air, secret ancient syllables that danced around the rooms, etched meticulously on my laboratory's stone floor. The energy of uncharted cosmos hummed at my fingertips, the very essence of potential that fuels the stars. It was then, in my fervor to touch the unknown, that the unexpected occurred. A sudden surge of energy interrupted me, the symbols on the floor blazing with an intense light. A low, resonant hum filled the room, rising in pitch until a swirling, ethereal portal opened in the center of the sigil. The portal pulsed with an unearthly energy, filling the room with a crackling anticipation. This was not the outcome I had intended. In my quest for power, I had inadvertently opened a door to another world. The symbols on the floor blazed with a fierce light, and the air hummed with a resonant energy that sent shivers down my spine. What in the realms? I stepped back, shielding my eyes from the brilliant light. "This is not what I intended," I exclaimed. From the portal, a shape began to emerge. My eyes widened in astonishment as a creature stepped through. An otherworldly dog, with sleek fur that seemed to shimmer with its own inner light. Its eyes, deep and intelligent, scanned the room with an inquisitive gaze. This was no ordinary dog. As it stepped cautiously from the swirling vortex, it seemed to carry with it the essence of the cosmos, an aura of intelligence and curiosity that defied its canine form. The dog tilted its head, sniffing the air, before locking eyes with me.
Hello, I am Quark 137.
I blinked, momentarily at a loss for words. A talking dog? Well, this is unexpected, I muttered at last. We stood there, staring at each other, the symbols on the floor, still glowing softly in the background, uncertain of what to expect next. There was a moment of mutual curiosity and wariness, a pregnant pause in the air, as if the very room held its breath. I had encountered many strange beings in my time, but a talking dog from another dimension was something entirely new, a revelation that left me speechless. What manner of being are you? I finally asked, recovering my composure, my voice barely a whisper. The dog sat down, its posture relaxed yet dignified, a sense of calm emanating from its being.
I could ask the same of you. What is this place? It looks like I have been drawn here by you.
I stroked my beard thoughtfully. Indeed, I was attempting to harness a new form of energy through a spell, but the consequences were beyond my wildest imaginings. The dog looked around the lab, his eyes reflecting both curiosity and a hint of caution, as if weighing the situation.
This is a powerful place. Are you a powerful wizard then?
I chuckled, the question making me pause, the gravity of the situation sinking in. Powerful, in some ways, perhaps. But what is power, truly? The atmosphere in the lab shifted from one of tension to curiosity and camaraderie. We were two beings from vastly different worlds, yet the question showed we were united by a common quest for knowledge and understanding. I am a wanderer, I said, extending a hand, the gesture a symbol of friendship and goodwill. He sniffed the offered hand before touching it with a paw. A moment of connection, a bridge between our worlds.
Pleased to meet you. In my dimension, I am called Quark 137, but you may call me just Quark.
My eyes lit up with interest. Fascinating. Your presence here raises many questions. Perhaps you can help me understand more about the powers that govern our existence. Quark 137's eyes sparkled with curiosity.
Power, you say? What do you know of power, wizard?
I gestured around my laboratory. Power is more than strength or control. It is the very fabric of reality, the forces that shape and sustain the universe. Quark 137 tilted his head, a gesture of curiosity, a silent question.
Then show me the most powerful things in this universe.
I nodded, feeling a sense of excitement. Very well, Quark. Let us embark on a journey through the cosmos to discover the true nature of power. Quark 137 wagged his tail, his eyes bright with anticipation, a sign of readiness, an eagerness for what lay ahead.
Lead the way. Let us uncover the mysteries of your universe.
And with that began our first journey. I led him first into a forest clearing, started a fire, and we sat there, letting the warmth seep into my old bones. There's something comforting about sharing stories with the flickering flames, as if the fire itself is a companion, listening intently to every word. Power, I began, letting the word hang in the air, like smoke from the fire, can take many forms. There is physical power, the strength of the body. Consider the might of a warrior, the force of a blow that can fell an oak, or the endurance to run for miles without faltering. It is tangible, measurable, and yet, in the grand scheme, it is but a fleeting gift. Time has a way of diminishing physical strength, wearing it down as waves wear down stone. Quark's eyes gleamed with interest, his ears perked as he listened. I could see the questions forming in his mind, the thoughts chasing one another. Then there is political power, I continued. The influence over others, the ability to shape the course of events, to lead nations and command armies. It is a formidable power, born of charisma, strategy, and sometimes ruthlessness. But political power is a double-edged sword. It can build empires, but it can also destroy them. It is subject to the whims of the masses, the tides of public opinion, and the schemes of rivals. I saw Quark nodding, understanding dawning in his intelligent eyes. He was beginning to grasp the complexity of power, its many facets and nuances, or perhaps already knew of it before and was showing his agreement. And let us not forget monetary power, my voice softening as I leaned closer to the fire. The wealth that can buy comfort, security, and even influence. Money can build cities, fund armies, and sway the hearts of men. Yet, it is an illusion, a construct of society. It can vanish in an instant, lost to bad decisions or the shifting sands of fortune. Quark's tail wagged thoughtfully.
But what about magic?
He asked, his voice a curious growl. Ah, magical power, I said, smiling. The energy that flows through all things, the essence of creation itself. Magic is a force beyond measure, capable of wondrous miracles. and terrible destruction. It is both a gift and a responsibility, a tool and a mystery. To wield it requires not just knowledge, but wisdom and a deep understanding of the world and oneself. I paused, looking up at the night sky. The stars shone like distant lanterns in the velvet dark. But even magical power pales in comparison to the true power of the universe. My voice barely above a whisper. The power that binds the stars, that drives the turning of the planets, and the beating of every heart. It is the power of creation, of life and death, of the endless dance of existence. It is beyond our comprehension, beyond our control, and yet it is within us, part of us, as we are part of it. Quark looked at me, his eyes wide with wonder.
So all these forms of power, they are just reflections of something greater?
He asked. Exactly, I said, nodding. They are but fragments, mere tokens, born out of the universe. True wisdom lies in recognizing this, in understanding that all power is but a small part of the vast, unfathomable whole. To wield power wisely is to be in harmony with the universe, to use it for the greater good, to seek balance and understanding. We sat in silence for a moment, the fire crackling softly, the night pressing close around us. I could see the weight of my words settling on Quark, the beginning of a new understanding, taking root in his mind. Come, I said, rising and reaching for my staff. There are places I want to show you, things I want you to see. We stepped out into the night, the cold air biting at our faces. As we walked through the forest, visiting ancient groves and hidden ruins, I couldn't help but reflect and wonder how fragile and vain our notions of earthly power were. The wind carried a chill as we stepped away from the fire's glow, leaving the forest behind. The ground beneath us gave way to a breathtaking cliff's edge where the sky seemed to stretch infinitely. The stars glittered there, like little diamonds, with no visible distractions. It was almost as if everything else had ceased to exist. Quark, I said, as the horizon began to lighten, let us begin at the beginning, or at least the beginning of as far as we can go with our present knowledge. Do you wonder how all of this came to be in this universe? Quark tilted his head, his eyes reflecting the shimmering sky.
Of course, where I come from, the view of the night sky is very similar to this, and I often wonder how it all started.
He replied. I knelt down, tracing a circle in the dirt with my finger. Imagine a single point, I began. A point so small, yet containing all the energy of the universe. This singularity exploded in what we call the Big Bang, marking the birth of everything. As I spoke, I conjured an image of the universe's birth in the air before us. In the first moments, the universe expanded rapidly. Energy transformed into matter, forming the first particles that became the building blocks of all we know. Quark's eyes widened.
How powerful was it?
He asked in awe. Unimaginably powerful, I replied. The energy released created all the stars, galaxies, and worlds. It was a force that set the cosmos in motion and continues to drive it forward. We stood in silence, the wind carrying the echoes of that primordial explosion. I watched the stars reflected in Quark's eyes, each a reminder of the incredible power that birthed them. Quark eventually asked,
How long ago was this?
I continued, roughly 13.78 billion years ago. The Big Bang didn't just create matter, it also established the laws of physics. These laws govern everything, from the formation of galaxies to the emergence of life. Quark nodded thoughtfully.
So, if everything we know in this universe came from this single point, was it the most powerful thing we can ever conceive?
Probably, I said, smiling. Gravity, nuclear forces, electromagnetic waves, and I will explain what these are later, are but the legacies of that first explosion, of that first point. We lingered there, feeling the universe around us. Quark, I said softly. We are all part of this grand universe. The atoms in our bodies were forged in stars, remnants of that original burst of creation. Everything we know of began then, or so we think. Quark gazed at me curiously.
So, there is some doubt?
Yes, I replied, placing a hand on his fur. There is always doubt, always other explanations. But this is the general consensus today. If you were to ask me, what is the most powerful thing we have ever known, that would be my answer. The whole universe, condensed into a single point. Quark looked up at the night sky, lost in thought.
What is the most powerful thing in the universe now?
I thought a while before answering. It really depends on what you see as one thing, or when. Even time can be relative, but that perhaps is a discussion for another time. Ironically, my eyes twinkling. Consider this. If a nuclear explosion took place in a city, would you consider that to be a display of energy and power in isolation? Or would you say that was part of Earth's power? The wrath of our sun, glowing away. Is that a thing of its own, or would you define it as the power of the galaxy? It sits within. You might think of space as empty, separating objects visually, but in reality, even that space is teeming with particles, invisible to the naked eye. Does that mean the sun and the earth are connected and should be seen as one object? Perhaps the whole solar system, maybe the whole galaxy. Quark grappled with that question before answering.
I begin to see the dilemma. Everything is connected to another.
He thought for a few more seconds before adding,
For simplicity's sake, let us identify these as distinct objects. We're separated by space, but perhaps also as part of something bigger too, as long as the bigger whole consistently has the same constituents across the universe.
I bowed my head to his wisdom. There definitely was a very intelligent being behind those eyes. Very well. Let us work with that assumption and explore the most powerful objects in the universe, following the Big Bang. But before we continued our journey, we stood beneath the infinite sky for a while. The power of the universe pulsed around us, and for those who could hear, singing a song of creation, life, and existence. I felt a profound sense of peace, knowing we were part of something far greater than ourselves. We left the cliff behind, walking into a forest where the trees seemed to whisper lightly in the wind. The path was lit by a million stars, illuminating our way forward. As we meandered through the trees, the atmosphere felt charged with the promise of discovery. Quark, I said, breaking the silence, let us now look to what the universe was like right after its birth, a story of the particles. Quark looked up, intrigued.
What do you mean?
Let me show you, I replied, conjuring a vision of the early universe. After the Big Bang, the universe was a hot, dense soup of energy. As it expanded, it cooled, allowing the first particles to form. Quark trotted beside me, ears perked.
What kind of particles?
I glanced at him. Surely you must know, for you seem to be named after one of them. Quark shook his head.
I had no idea.
The most fundamental ones, quarks and leptons, I explained. These particles combined to form protons and neutrons, the building blocks of matter. Picture a chaotic dance, particles colliding and merging, driven by the universe's intense energy. We reached a clearing where the ground seemed to shimmer, and I waved my hand, summoning a vision of that primordial dance. Tiny particles flickered and darted, colliding and merging in a frantic, beautiful chaos. I carried on. As the universe continued to cool, protons and neutrons combined to form the first atomic nuclei. This era is known as nucleosynthesis. Hydrogen and helium, the simplest atoms, emerged during this time. Quark watched the vision with rapt attention.
So, the atoms that make up everything were formed then?
Yes, I said, smiling. The atoms that compose stars, planets, and even our own bodies were forged in those early moments. It's humbling, isn't it? We are made of the same stuff, created in the fires of the cosmos. The vision dissipated like morning mist. As we walked on, the path leading us to a tranquil pond I sat at its edge, motioning for Quark to join me. But the story doesn't end there. I said, my voice soft. The universe continued to evolve. Atoms drifted through space, pulled together by gravity. Over time, they formed clouds of gas, waiting for the spark of creation. Quark sat beside me, his gaze fixed on the pond's surface.
What happened next?
In these clouds, gravity continued its work, compressing the gas until the pressure and temperature reached critical levels. It was in these stellar nurseries that the first stars were born. Nuclear fusion began, turning hydrogen into helium, releasing light and heat, and illuminating the darkness. I paused, letting the significance of this moment sink in. These first stars were the beacons of the early universe. They created heavier elements through fusion, spreading them across the cosmos in supernova explosions, seeding the universe with the building blocks for planets and life. Quark looked up at me.
So, the universe's power is also in its ability to create and transform?
Exactly, I said. The universe is a flow of creation and transformation. The power of the Big Bang set everything in motion, but the ongoing processes of star formation, fusion, and supernovae continue to shape and evolve the cosmos. As we sat there, the night deepened, and the stars shone brightly above, casting a beautiful light across two unusual companions, lost in their thoughts. We moved away from the pond, wandering into a field where the grass swayed gently in the starlight. Here, in the quiet of the night, I prepared to reveal another secret of the universe. Quark, I began as the stars twinkled above. Let me show you something incredible. The cosmic microwave, background radiation. It's the universe's baby picture. Quark's ears perked up.
What is that?
I smiled and gestured to the sky. Imagine the universe shortly after the Big Bang. It was hot, dense, filled with a plasma of particles and radiation. As it expanded, it cooled, allowing protons and electrons to combine into neutral hydrogen atoms. This moment, known as recombination, happened about 380,000 years after the Big Bang. I waved my hand, and an image appeared in the air, a map of the sky unlike any other. This is the cosmic microwave background radiation, or CMB. It is the afterglow of the Big Bang, light that has traveled through the universe since recombination, cooling and stretching as it went. Quark stared at the map, eyes wide.
So, this is what the universe looked like back then?
Yes, I replied. The CMB is a snapshot of the universe when it was just 380,000 years old. The tiny fluctuations in temperature and density are the seeds of all the structures in the universe galaxies, stars, planets. Quark gazed at the image in awe.
Why is it important?
The CMB holds a wealth of information about our early universe. I explained. By studying it, scientists have learned about the universe's age, composition, and rate of expansion. It is a sort of blueprint, guiding us in understanding the mysteries of the cosmos. Quark nodded thoughtfully.
So this faint glow is from the Big Bang?
Exactly, I said softly. It is the echo of creation, a reminder of the immense forces that set everything in motion. The CMB is a record of the universe's beginnings, a silent witness to the birth of everything we know. We stood in silence for a while, the stars above seeming to pulse in time with the ancient light. Come, I said gently. Let us continue our journey further, with the CMB as our guide. The night grew deeper as we journeyed through a valley where shadows danced under the starlit sky. The path led us to a high ridge, and in the distance, a nebula blazed with the birth of new stars. This was our destination, a cosmic nursery where creation was in full swing. Look there, Quark, I said, pointing to the glowing cloud of gas and dust. That's a stellar nursery, where stars are born. Quark's eyes sparkled with excitement.
How does it happen?
I rummaged through my robe and pulled out a telescope, big enough for both of us to peer into. Through the telescope, we watched as gravity pulled gas and dust together, forming dense cores. Gravity is the architect, I explained. It compresses these materials until the pressure and temperature are so high that nuclear fusion begins. That's when a star is born. Quark peered through the telescope, watching the process unfold.
So, stars are like natural reactors?
Exactly, I said. In the core of each star, hydrogen fuses into helium, releasing immense energy. This process, called nuclear fusion, powers the stars and produces light and heat. I conjured an image of the fusion process, showing hydrogen nuclei combining to form helium. Every second, our sun converts millions of tons of hydrogen into helium, releasing energy that sustains life on Earth. Quark's eyes gleamed with understanding.
So, stars are incredibly powerful.
Indeed, I replied. The energy produced by stars through fusion is what lights up the universe. As stars age, they fuse heavier elements, creating the building blocks of planets and life. When they exhaust their fuel, they often end their lives in spectacular supernova explosions, spreading these elements across the galaxy. For a while we watched in silence as the stars in the nebula continued to form, their light growing brighter. And then finally, I placed a hand on his fur, feeling a deep connection to the cosmos and to this curious, intelligent being beside me. Come, I said warmly, there is still more to explore, more to learn. We wandered from the ridge, descending into a landscape bathed in moonlight. The vastness of the sky above made everything seem both intimate and infinite. As we reached a high plateau, the night air crisp, I prepared to share the story of a star particularly close to us. Quark, I began, as we found a spot to sit. Let's talk about the sun. Quark's eyes brightened with recognition.
The sun? Is that a star around which everything revolves in this solar system?
I looked at him curiously. And how do you know that? Is it the same where you come from? Quark paused before answering.
From everything you have been showing me, it looks like we live in a dimension overlapping each other. Although we do not possess as detailed a knowledge of the cosmos as you do, I think we might actually be from the same universe.
Fascinating. So is everything exactly the same as it is in your dimension? Quark paused again.
Not quite. For one, I could move in more than 3 different directions there. It is a strange feeling to be so limited here. We also have more particles that seem to disappear and appear in random places, unlike here, where everything feels more stable. Unfortunately, we don't have the magic or technology to explore and understand everything you have been explaining. But I think it might be the very same sky and solar system you have been describing.
I looked at him more closely. Interesting theory. What is the most powerful thing in your dimension then? Quark smiled broadly.
I think it might be easier to explain once you have covered everything in this dimension first.
I see, I said. Very well. Let us continue then. Going back to the sun, it is the heart of our solar system, a colossal fusion reactor that provides the energy necessary for life on Earth. It is a perfect example of the power of nuclear fusion in action. I conjured a shimmering image of the sun before us, its surface roiling with activity. The sun is a medium-sized star, but its power is anything but modest. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing an incredible amount of energy. Quark's ears perked up, his tail wagging slowly.
How much energy?
To put it in perspective, I said, my eyes reflecting the glowing image. The sun's energy output is about 3.8 times 10 to the power of 26 watts. This is equivalent to the detonation of 91.92 billion megatons of TNT every second. The sun's power is so immense that it could meet the energy needs of Earth's entire population for millions of years in just a single second. Quark's jaw dropped slightly, his eyes wide with awe.
That's unimaginable.
Yes, I agreed, smiling. And that is just the constant output of the sun. There are moments when the sun releases even more energy in the form of solar flares. I waved my hand, and the image of the sun zoomed in, highlighting a region where a massive flare was erupting. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy stored in the sun's atmosphere. They can release as much energy as 1 billion hydrogen bombs exploding simultaneously. Quark's eyes were fixed on the image, his tail now still, as he absorbed the information.
What causes these flares?
He asked, his voice a mix of curiosity and concern. The sun's magnetic field is incredibly complex and constantly in motion, I explained. When magnetic field lines twist and snap, they release vast amounts of energy in the form of light, heat, and radiation. These flares can affect space weather, disrupting communications and navigation systems on Earth, and can pose a risk to astronauts and satellites. The image shifted, showing the flare's energy spreading out into space, a wave of electromagnetic radiation racing across the solar system. The most powerful solar flare ever recorded, known as the Carrington event of 1859, caused telegraph systems to spark and fail, and auroras to be seen as far south as the Caribbean. If a similar event were to happen today, it could cause widespread technological disruptions. Quark looked up at me, his eyes filled with both wonder and a hint of apprehension.
The sun is powerful and dangerous,
he said, his voice thoughtful. Yes, I said, nodding. But it is also the source of life. Without the sun's energy, our planet would be a frozen wasteland, devoid of life. The sun's power is a reminder of the delicate balance that sustains us and of the immense forces at work in the universe. We stood there, gazing at the image of the sun, its surface alive, with the dance of plasma and light. After a while, I decided it was time to get going again. We walked on for a while and came across an empty field, completely insulated from the noise and pollution of a city. It was there that I decided it was time to share the story of the life of stars. Quark, I said, pointing to the night sky. Let's explore the lives of stars, their lifespans, and how they depend on their mass and power output. Quark's ears perked up. His curiosity rekindled.
Stars have lifespans? Like living things?
Exactly, I said, smiling at his innocent question. Stars, much like living creatures, have beginnings, middles, and ends. You have already seen how they are born. Their lifespans, however, are determined by their mass and the rate at which they consume their nuclear fuel. We reached a grassy knoll, and I gestured for Quark to sit beside me. I conjured an image in the air, a stellar nursery filled with stars, of varying sizes and colors. Stars are born from vast clouds of gas and dust, as we've seen, but once they ignite, their fate is sealed by their mass. The most massive stars burn brightly and live short, tumultuous lives, while smaller stars shine steadily and might live for billions of years. Quark tilted his head, listening intently.
Why do the massive stars have shorter lives?
Their immense power output, I explained. Massive stars have a greater gravitational pull, leading to higher core temperatures and pressures. This causes nuclear fusion to occur at a much faster rate, consuming their hydrogen fuel more quickly. For instance, a star 10 times the mass of our Sun might only live for 20 million years, whereas our Sun, with its moderate mass, will shine for about 10 billion years. I shifted the image to focus on a particularly massive star, its surface roiling with energy. A star like this, with 50 times the mass of the Sun, will burn through its fuel in just a few million years. These stars are incredibly powerful, producing energy at a rate millions of times greater than our Sun. Their brilliance is due to the ferocious pace of their fusion reactions. Quark's eyes widened as he absorbed this information.
So, the more massive the star, the shorter its life because it burns its fuel faster?
Precisely, I said, nodding. The luminosity of a star, which is a measure of its power output, increases dramatically with mass. A star that is twice as massive as the Sun is not just twice as bright. It can be up to 10 times as bright, or even more. This exponential increase in luminosity means that more massive stars exhaust their fuel quickly. I conjured another image, this time of a smaller, red dwarf star. On the other end of the spectrum, we have red dwarfs, small, cool stars with much lower mass and power output. These stars burn their fuel so slowly that they can live for tens to hundreds of billions of years, far longer than the current age of the universe. Quark's tail wagged thoughtfully.
So, red dwarfs are like the tortoises of the stellar world, slow and steady?
Exactly, I said, smiling at the apt comparison. Their low mass means they have lower core temperatures and pressures, leading to a slower rate of fusion. They are the most common type of star in the universe, quietly burning away for eons. I gestured to the sky, highlighting different constellations. The mass of a star not only determines its lifespan, but also its eventual fate. Massive stars may end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. Smaller stars, like our Sun, will swell into red giants before shedding their outer layer and leaving behind a dense core known as a white dwarf.
What are supernova, neutron stars, and black holes?
He asked. I looked at him gently and said, apologies. I seem to be jumping ahead. We'll cover these later in our journey. Quark looked up at the night sky, his eyes reflecting the myriad stars.
So, the mass of a star sets the stage for its entire life and its death?
Yes, I said, my voice filled with the awe I felt every time I contemplated these celestial truths. The mass of a star is its destiny, It dictates how brightly it will shine, how long it will live, and how it will meet its end. We sat in silence for a moment, the night around us filled with the distant hum of stars, living out their varied destinies. Finally, we got up again, and the journey brought us to a quiet, secluded spot. The stars overhead were brilliant, each one reflecting the beauty of the universe. As we settled on a hilltop, the night air cool and crisp, I prepared to share with Quark one of the most dramatic and awe-inspiring events in the life of a star. Quark, I began, my voice tinged with reverence. We have spoken of the birth and life of stars. Now, let us explore their death, specifically the cataclysmic event known as a supernova. Quark became still and somber at this.
The death of a star? I suppose that even the brightest lights must eventually fade. But that does sound powerful.
It is, I said, nodding. A supernova marks the end of a massive star's life, and the energy released in such an event is staggering. Imagine a single star outshining an entire galaxy. This is the power of a supernova. I conjured an image in the air before us, a massive star in its final throes. When a star many times the mass of our sun exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. The core collapses in a fraction of a second, causing a tremendous release of energy. The image showed the core imploding, followed by an explosion of light and energy that radiated outward. This collapse triggers a shockwave that blasts the star's outer layers into space. The energy released is so immense that for a short period, the star can outshine an entire galaxy. To put it in perspective, a supernova can release as much energy in a few seconds as our sun will produce over its entire 10 billion year lifetime. Quark's mouth opened slightly, his eyes wide with awe.
That's incredible. How much energy are we talking about?
A typical supernova releases about 10 to the power of 44 joules of energy, I explained. This is equivalent to the energy output of 10 octillion nuclear bombs. The light from a supernova can be seen across great distances, sometimes even in other galaxies. For example, supernova 1987A, which occurred in the Large Magellanic Cloud, was visible from Earth with the naked eye, despite being about 168,000 light-years away. I shifted the image to show the remnants of a supernova, a beautiful, expanding nebula of gas and dust, glowing with the light of newly formed elements. But the supernova is not just an end, it is also a beginning. The explosion creates and disperses heavy elements like carbon, oxygen, and iron into space. These elements are the building blocks of planets and life. In a very real sense, we owe our existence to these stellar explosions. Quark's tail wagged slowly as he took in the sight.
So, supernovas are both destructive and creative?
Precisely, I said, smiling at his insight. They are the universe's way of recycling material, spreading the ingredients for new stars, planets, and ultimately, life. The death of a star sows the seeds for future generations. I conjured an image of a neutron star and a black hole, the possible remnants of supernovae. Depending on the mass of the original star, the core that remains after a supernova can become either a neutron star or a black hole. Neutron stars are incredibly dense, packing the mass of the sun into a sphere just a few kilometers across. Their gravity is so intense that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. Quark's eyes widened even further.
And black holes?
Black holes, I said, my voice dropping to a whisper, are regions of space where gravity is so strong that nothing, not even light, can escape. They are the ultimate endpoints of massive stars, regions where matter is crushed to infinite density. The energy required to form a black hole is beyond comprehension, but they too play a crucial role in the universe, influencing the formation and evolution of galaxies. We sat in silence for a moment, the enormity of these cosmic events settling over us like a blanket. The stars above seemed to pulse with the echoes of ancient supernovae, their light a reminder of the powers that shape the universe. We wandered from the hilltop, arriving at a stone bridge over a river, reflecting the universe above. We sat there, looking up at the stars, shining brightly above. Let's look at the neutron stars in detail at first. Neutron stars, conjuring an image of one in the air before us, are the incredibly dense remnants left behind after a supernova. When a massive star explodes, its core collapses under gravity, crushing protons and electrons together to form neutrons. The result is a star made almost entirely of neutrons, packed into an incredibly small volume. I let the image rotate slowly, showing the dense, compact nature of a neutron star. To give you a sense of their density, imagine compressing the mass of the sun into a sphere just about 20 kilometers in diameter. A sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. Their gravity is so strong that it warps space and time around them. Quark's jaw dropped slightly, his eyes reflecting the awe I felt every time I contemplated these stellar remnants.
That's so dense. How powerful are they?
Neutron stars are incredibly powerful, I continued. Their surface gravity is about 2 billion times stronger than Earth's gravity. This means if you were to drop an object from just 1 meter above a neutron star's surface, it would hit the surface at around 4.3 million kilometers per hour. The energy released in such impacts is immense, making neutron stars some of the most extreme objects in the universe. I shifted the image to focus on a pulsar, a type of neutron star. Some neutron stars become pulsars, which are neutron stars with powerful magnetic fields that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep across space, and if they point towards Earth, we see regular pulses of radiation, hence the name pulsar. Quark's ears perked up, his eyes transfixed on the image. Pulsars are like cosmic lighthouses, I continued. They spin incredibly fast, sometimes hundreds of times per second. This rapid rotation, combined with their strong magnetic fields, makes them emit beams of radiation with astonishing regularity. The fastest known pulsars, called millisecond pulsars, can rotate over 700 times per second. I conjured an image of a pulsar, showing its intense beams of radiation sweeping through space. The power of a pulsar's radiation is immense. A typical pulsar emits more energy in 1 second than the sun does in a year. The regularity of these pulses is so precise that pulsars are used as cosmic clocks, helping astronomers measure distances in space and even detect gravitational waves. Quark's eyes gleamed with understanding.
So, pulsars are not just powerful, but also useful for studying the universe?
Exactly, I said, smiling at his insight. Pulsars have helped us learn about the fundamental laws of physics, the behavior of matter under extreme conditions, and the structure of our galaxy. They are powerful beacons that illuminate the dark corners of the cosmos. I paused, letting the significance of these stellar remnants sink in. The night around us seemed to hum with the energy of these distant, powerful objects, a reminder of the incredible forces at play in the universe. Eventually, I said, "Let us move on. There are other things I would like to show you." Quark nodded. Together, we rose and walked into the night, under the light of the stars, still full of life. Our path led us to a secluded valley, where it seemed the wind was bellowing hard, almost as if it was being sucked into something, somewhere far away. This was apt, as it was there that I prepared to share with Quark the final chapter in our exploration of stellar remnants, the mysterious and powerful black holes. "Quark," I said as we sat down on a nearby boulder, "we have seen the birth and death of stars, the creation of neutron stars and pulsars. Now let us explore one of the most enigmatic and powerful remnants of all, black holes." Quark looked up.
If what you said is true, and they can trap even light, they must be incredibly powerful.
"Indeed, they are," I said, conjuring an image of a black hole in the air before us. Black holes are the remnants of the most massive stars, those that were once at least 20 times the mass of our sun. When such a star exhausts its nuclear fuel, it undergoes a supernova explosion, and its core collapses under the force of gravity, creating a black hole. The image showed a massive star collapsing, followed by the formation of a black hole, a region of space so dense that its gravity prevents anything, even light, from escaping. Black holes are often called the ultimate power sinks because of their immense gravitational pull. I continued. The boundary around a black hole, known as the event horizon, marks the point of no return. Once something crosses this threshold, it is irrevocably drawn into the black hole. Quark's ears perked up, his tail wagging thoughtfully.
How strong is their gravity?
The gravity of a black hole is so strong that it warps space and time around it, I explained. For instance, a black hole with the mass of our sun would have an event horizon with a radius of about 3 kilometers. The gravitational pull near this event horizon is so intense that time itself slows down relative to an outside observer. I conjured an image of a spacecraft approaching a black hole, illustrating the effects of gravitational time dilation. If you were to watch someone falling into a black hole, you would see their time slow down and eventually freeze at the event horizon. To them, however, time would continue normally, and they would fall into the black hole in a matter of seconds. Quark's eyes widened, his mind grappling with the concept.
That's mind-boggling. How much energy is involved?
Black holes are incredibly energetic, I said, my voice filled with awe. When matter falls into a black hole, it forms an accretion disk, heating up to millions of degrees, emitting X-rays and gamma rays. The energy output of this process can be greater than the combined light of all the stars in a galaxy. The supermassive black holes at the centers of galaxies, like the one in our Milky Way, can have masses millions to billions of times that of our sun, and can release immense amounts of energy. I shifted the image to show a supermassive black hole at the center of a galaxy, its accretion disk glowing brightly. These supermassive black holes power quasars, which are some of the brightest objects in the universe. A single quasar can outshine thousands of galaxies combined, with an energy output of up to 10 to the power of 40 watts. Quark's eyes were wide with wonder.
So, black holes are not just power sinks, they're also power sources?
Precisely, I said, nodding. They are both destroyers and creators, shaping the galaxies around them. The gravitational influence of black holes helps regulate star formation and can even drive the evolution of entire galaxies. I conjured a final image showing the complex interplay between black holes and their surrounding galaxies. Black holes are a reminder of the incredible power and mystery of the universe. They challenge our understanding of physics and push the boundaries of what we know about space and time. Quark nodded, his eyes reflecting the starry sky.
Amazing. Just amazing. It's all so incredible and humbling.
It is at this point, perhaps, we should take a break from the retelling of this story, a moment to let our minds rest and absorb the wonders we have uncovered today. In storytelling, as in life, breaks are essential. They allow us to reflect, to let the weight of the information settle, and to prepare ourselves for the next leg of the journey. And make no mistake about it, our journey to explore the most powerful forces in the universe had only just begun.